Okay, this will be discussion of section 1.2 of the textbook, Numerical Methods for Engineers and Scientists, basically discussing how to represent numbers in a computer system. Everybody's pretty familiar with base 10. So just going straight from your textbook, because I have a decent example, it's not a very problematic idea. The base 10 comes from the fact that you're using 10 as the base of the exponent. So as we go up, the exponent value starting at 10 to the 0, which is of course 1. 10 to the first, 10, 10 to the second would be 100, 10 to the third is 1,000, etc., etc., all the way up, 10 to the fourth, 10 to the 10th, whatever, however high or low you want to go, you represent that component of the total number as base 10. 10 is the base exponent, thus the name of that system. So to represent the value here, 60,724.3125, it's very straightforward. You have 6 in the thousandth spot, 6 in the 10,000th spot, 0 in the 1,000th spot, 7 in the 100th spot, 2 in the 10 spot, 4 ones. So 6 $10,000 bills, 0 $1,000 bills, $700 bills, 2 $10 bills, and $4 bills. But end up doing the same thing down here, except you're devaluing. So this would be tenths, hundredths, thousandths, 10,000ths. And that's what we've been hearing ever since high school, dealing with the metric system, dealing with all the different abbreviations. So you have all the deca, centi, milli, all these different prefixes that deal in the base 10 number system, because especially SI is based in that very, very heavily. So that's base 10. We're very, very used to dealing in that system, doing all of our mathematics in it. The thing that is a bit less intuitive is base 2. So just to skip straight to an example, let's go to the middle of the page and I'll discuss some of these things up top next. Base 2 is a bit more odd, and this is useful in that we can represent the presence or absence of a number by a switch. Obviously, this is going in the direction of numeric discussion. The absence or presence of a logical value saved on your hard drive and your memory and whatever memory storing device or calculated state is all you need to represent very large, very small numbers. We'll go through the whole range of feasibility. So in this case, instead of using 10 as the base, we have 2's everywhere. 2 to the 0, 2 to the first, 2 to the second, etc., 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 all the way up to the fourth, 2 to the 50th, however high or low you care to go in your system. It just takes more bits. If you have a 64-bit computer, it has more switches that can represent numbers than a 32-bit computer. So it by definition is more precise. It can be more precise. And by definition, one of the big advantages of 64-bit systems is they can have more addressable memory locations, which takes the memory ceiling RAM way, way higher on 64-bit base operating systems. So that was one of the big incentives once we got into the multi-gigabyte RAM possibilities. So anyway, in this system, 2 to the 0 is obviously still 1. 2 to the first is of course 2. 2 to the second, 2 squared is 4. 2 to the third, that'd be 4 times 2, so that'd be 8. Then 2 to the fourth, you get all the way up to 16. So this just keeps stepping up and stepping up and stepping up and stepping up. And so I have a whole table of this made in Excel. So this is base 2. And that's the answer here on the right. So it's just 2 to the exponent listed in this left column. So 2 to the 0th is 1. 2 to the first is 2. 2 to the second is 4, just like we've gone through. But now you can make this very simple. That 2 to the 16th is 65,536. And it just keeps going. If you want to go up to 17, you can say equals 2 to the 17th power, 131,072. And what's interesting is you can form any number you want out of combinations of these. In fact, if we go back to the textbook, you see up here in the top left, they have the first 10 numbers represented in base 2. So it's actually a rather simple thing to do if you've not gone through this before. You just start adding up all the different components. If you had a binary digit, which let's just cover up everything but that first row for a second. So if you want to represent 1, you basically need one whole switch. 2 to the 0th is 1. That's your whole value, so you do not want to add a 2 to it, you don't want to add a 4 to it, you don't want to add an 8 to it. Not a big deal. Pretty simple. If you want to represent 2, well, you can do that with still a single switch, but this time you would do that with the second bit. Each one of these switches and memory locations represent a bit. So 2 to the 0th would be off. 2 to the 1st is 2. That represents the full value you're seeking, so no need to switch on any 2 to the 2nd or 2 to the 3rd. You can see this table just continues going all the way down. You'll recognize the pattern relatively quickly. Once you get essentially bit saturation, like on 3, you would turn off both the first switch and the second switch, so 2 to the 0th and 2 to the 1st, making a total value of 3. And guess what? When you go up in increment to 4, you flip those previous 2 off and you just flip the next one on. This lends itself to some very simple transistor-based logic that allows computers to add binary numbers relatively easily, especially count in binary relatively easily. So then you just see it start ticking away again. So you get 1 in the 2 to the 0th, then it shifts to 2 to the 1st, then you fill up both segments, and once you see that all 3 of those states are populated, guess what? It shifts up to 2 to the 3rd. So as we know, 2 to the 3rd is 8, so that means there's only one switch required to represent the number 8 in base 2. It would be the 4th bit. Of course, understanding the placement of all these is very important. Then you can go all the way up to 10 right here. In fact, the number that would be created by turning all 4 of those on is an interesting thing to question. So it would be 1 plus 2, so we're at 3, then plus 4, which would take it to 7, and then plus 8. So 8 plus 7, that'd be what, 15. So with 4 bits, you can have 15 different colors. You can have 15 different outputs. So if you've ever seen a terrible old 16 color display or a 4 color display, you can back out how many bits they were using. So anyway, you can combine this not only to positive exponents but to negative ones as well when you need fractional portions of a whole number. So if I go back to my big table that I made for you for a moment, I've also extended this to negative exponents, negative 1, negative 2, negative 3, negative 4. This is obviously not something you would want to create and determine on your own because you're basically taking roots of all these values. It's much easier to just do the positive exponents than the negative ones. With the calculator, anything's possible, but then you're using a numeric problem to solve a numeric problem, so I don't know, is that self-defeating? Anyway, negative 1, 2 to the negative first would be 0.5, 2 to the negative second is negative 0.25. Not a big deal. You can see the formula I'm using here. Not a problem at all. This is just nice to see this in tabular form. No reason you have to stop at negative 16. You can go as far down or as far up as you care in exponents, and that's essentially just changing the bit depth of that system. So essentially these become building blocks so you can piece together to make any number you care to. The biggest singular block you have is 131,072. The smallest singular block you have is 1.5 times 10 to the negative fifth. If you're not familiar with this notation, E, capital E, you'll see that a lot in this class, stands for times 10 to the, in this case, it's negative fifth. So in this case, the smallest number that we can represent, if we restricted ourselves to 2 to the negative 16th, 2 to the positive, well, I'll take 17 off there, so that way it's symmetric. 2 to the positive 16th, the smallest possible number would be 1.5 times 10 to the fifth. The largest possible number, if we restricted ourselves to 2 to the 16th, you might think immediately, oh, the largest we can represent is 65,536, but think about it. It's actually the sum of all of the states. So if you turned every one of these on, it'd be the sum of every possible number, and that's 131,072. Coincidentally, if you remember what this number up here was, that's not just a mistake. Once you turn on all of the states, it is very close to being supplanted by the next binary state above it. And then you reobtain all of this counting resolution first in turning on this bit, and then you turn that off and go to this one, then you turn both of them on, then it just cascades up and up and up as you count at whatever resolution you would choose to perform that counting operation at. So this is base 2. To look exactly at how a longer number is put together, let's look down here at the representation from your textbook of 60,724.3125. They have all the mathematics laid out beneath you. But again, notice this is base 2. So we're taking the base number at different exponents, and those essentially become our building blocks that we're turning on or off with switches. These ones and zeros could literally be physical switches. They could indicate the presence or absence of this block of a particular height. However you want to think about it, that's basically the bit. This stream of data is what would be stored on your hard drive in binary form at some address location that your computer can call back up at just obscenely high speeds to allow you to figure this problem out. So in this case, we'd have 1 times 2 to the 15th plus 1 times 2 to the 14th plus 1 times 2 to the 13th. Now notice everything is either 1 times or 0 times. There's no possibility for you to have 3 times 2 to the 13th. Nope, it's a state. It's either there or it isn't. Those are your only options. So this all just gets summed up. So if we can remember that we're looking for 60,724.3125, we'll go back to my handy dandy little element here. We're going to do this manual summation. So if we say it had 1, it only went up to 2 to the 15th, so let's say equals the 2 to the 15th value plus 2 to the 14th was turned on. I'm reading this right out of the book. Plus 2 to the 13th plus 11th and 10th are also on. Notice we skipped the 12th, 2 to the 12th, because it's not required to make this data. See here, next would be 8, followed by 5 and 4. Now remember, these are 2 to the 5th, 2 to the 4th. The values are right there on the screen. 2 to the 2nd. And then 2 to the negative 2nd and negative 4th. And you just say, oh, equals, and you see 60,724.3. Doesn't seem quite right, does it? But if you notice, this is an Excel type gotcha. So if we go to formatting and have it actually show us the rest of the precision that Excel is calculating, you see that it's actually representing that number exactly as the textbook describes. 60,724.3125. So that is the binary representation. You essentially turn on 15, 14, 13, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1. Sound like Bender. But that's what it is. That's how they communicate with each other. This allows us to transmit, like, say you're working with radio communication, so you're working with, it doesn't even have to be a wired communication. If you just transmit these digital signals, and if the receiver's ready to receive that, it receives that binary stream, error checks it, converts it to a number, and congratulations, you've got a space program once you combine billions of those type of operations. Okay, that is binary representation in a nutshell. Please do read your textbook. It's quite straightforward on how to perform that.